All right, thank you all for coming. It's always nice to get a chance to talk a little bit about what you do to people who aren't your close friends and co-workers. A special word of gratitude, I suppose, to Elliot for making all of this possible and really stepping up for the SETI Institute when it really mattered. I'm going to talk about Kepler. This was originally going to be a highly technical talk, which was focused on people who already knew what I was talking about. I've tried to expand it out and give you some sort of a general flavor of the Kepler Space Telescope, its mission, its properties, and so on. You might notice a couple of seams where I've sort of switched from one talk to the other. If you get lost in the middle, don't worry, I'll come back up for air at the end. I'm specifically going to talk about the planet candidate catalog, which is the list of things that we found with Kepler which we think to be planets. This is the 7th of a series of catalogs we put out. The first 2 were put out by Bill Barucki, and then a number of us along the lines have worked on these as we've gone on. This 7th catalog is led by a gentleman by the name of Jeff Coughlin, who should be giving this talk since it's his catalog, but ironically, he can't come to Microsoft because he's in Seattle at the moment. And of course, this work, I have the 3 names up here, the 3 people who contributed most to this catalog. There is, of course, a team of people who have helped us understand the properties of our data, understand the properties of our systematics and all the problems we have in it. We refer to those people as the TCERT team, which is our own particular acronym. There's about 20-25 people who directly go into making these catalogs, and a cast of about 100 people who make the Kepler mission a success. Where do I point this? OK, so motivation. What's the big buzzword these days? It's big data, right? I'm going to try and make this a big data talk. I'm going to fail, but I'm going to try. This is some really big data. This is a picture of the oldest, the furthest, and the faintest objects ever laid eyes on by mankind. It's called the Hubble Ultra Deep Field. It was taken by the Hubble telescope. They basically took the darkest patch of sky they could find. They pointed the telescope there. They opened the shutter, and they exposed for about a month. And when they downloaded the data, this is what they saw. And it is truly, it's a beautiful picture. And if you look closely, you see that? That's a galaxy. There's about 100 billion stars there. That's a galaxy too. That's 100 billion stars. In fact, if you look at this in detail, with the exception of like 3 or 4 objects in this picture, every single object in here is a galaxy. Is about 100 billion stars. That's big data, right? There's a lot of stars there. And this is a really small patch of sky. If you took like a grain of salt or a grain of sand, hold it between your finger and your thumb, stretch out at arm's length like this, it's going to cover a bigger patch of sky than what this image is showing. The whole sky looks like this, and this is just a tiny, minuscule, minute fraction of it. So if you add it all up, there's probably about 100 billion galaxies out there in the observable universe. 100 billion galaxies, 100 billion stars in each galaxy, that's a lot of stars. And so it inevitably prompts the question, is our star the only star that has a planet around it that supports life? And you can take this from any perspective you want. You can say that life is this amazingly complicated, fantastic thing. The chances of it arriving are probably something in 1 in hundreds of billions, so we might be the only one. Or you might say that life shows up everywhere we look. It might be really common. But it's one thing to ask these questions, it's one thing to offer your opinions. It's quite another to actually answer them. And that was one of the goals of the Kepler mission. So to put this into perspective, way back in 1962, Frank Drake, who's one of the founder members of the SETI Institute, put together an equation to estimate the number of intelligent civilizations in the galaxy that could be communicating with us by radio waves. Listening to radio communications from other civilizations in the galaxy is sort of a core mission of the SETI Institute. And so he broke this down. This is not a rigorous equation that you learned in maths class. This is sort of a section headings for a discussion. This is the way it was intended. But he starts off, he says, you've got the number of stars that form per year, you've got the fraction of those in which planets form around them, the number of Earth-like planets, the fraction of those which form life, and so on. Specifically, the Kepler mission is interested in 2 of these numbers. It's interested in the fraction of planets, the fraction of stars that host planets, and the number of Earth-like planets around each star. In our own solar system, depending on who you ask, the number of Earth-like planets is 1, or it's 3. Some people consider Venus and Mars close enough to the Earth that you should say that they're Earth-like. So that depends on your point of view. We don't make any effort to address any of these other questions in the equation. Specifically, we have no ability to give you any insight into whether these planets actually host life or not. And that's an important thing to remember. If this is the only time you're going to hear from someone involved in Kepler, and everything else you're going to hear is on social media. We'll get back to social media. All right, a definition. This has caused us all sorts of trouble in the past. And we say we're going looking for Earth-like planets. We're going looking for habitable planets. We're going looking for another Earth. What do we mean by that? I'm going to define, for the purpose of this talk, what I mean by Earth-like, and I'm going to define it very narrowly. And I'm going to explain why I explain it narrowly in a few minutes. So a planet is Earth-like if it's about the same size as the Earth and it's got about the same surface temperature of the Earth. Size is important. If a planet is too big, it's probably a gas giant planet. In fact, it's almost certainly a gas giant planet. It's got no solid surface. So it's not a planet like our own Earth. And that's sort of an important thing we think for life. If we're going to go look for life, we're going to look for it in somewhere that looks somewhere like the Earth. That just seems like the easiest place to start. On the other hand, you don't want your planet to be too small. Your planet is small like Mars or the Moon. It doesn't have enough gravity to hold onto an atmosphere. And we think atmosphere is a very important thing for life too. The other requirement I have is temperature. And temperature actually corresponds into basically distance away from the star. If you've got a planet which is close into its parent star like Mercury, or even closer again, it's receiving too much energy from the star, it's too hot, all the water will boil off. And if there's one thing everyone I have talked to about life on other planets insists is important, it's water. Everything else seems to be negotiable by someone, but water is essential. On the other hand, if you go too far out, if you're out like Jupiter, Saturn, Uranus, Neptune, it's too cold. Any water you have will turn to ice. It's not going to be available for biology. So those are the two things I'm going to require. And I've listed here on the right-hand side a whole bunch of other things which you might reasonably consider to be important in the definition of a habitable planet, an Earth-like planet, which I'm not going to worry about. Whether there's water there or not, I don't talk about. I only talk about if the temperature is right for it. Whether there's an atmosphere, whether there's geological activity, people think that's important. Some people think some even more subtle concerns, like the rotation rate of the planet is important, whether it has a big moon, whether there's a gas giant planet for it out in the solar system, the stellar system. Some people have argued these things are important. I'm going to ignore all of them. I'm even going to ignore something which is considered by many people to be very important, is I'm going to ignore exomoons. These are moons around extrasolar planets. If you look at, you may have heard of Europa and Enceladus in our own solar system, where they're outside the habitable zone. They're too far away from the star to be to meet my definition. They're too small to have atmospheres, and yet people believe there may be liquid water on the surface of those. These might be very good places to go look for life. There are people who want to send probes to these moons to go look for life. But for the purpose of this talk, just to keep things nice and simple, I'm going to ignore them. OK, so how do we find planets? And you might think we've got this Hubble Space Telescope. It can see these galaxies which are 10 billion light years away. It should be easy to go find a planet, right? Planets aren't that faint. And planets aren't that faint. The Hubble Space Telescope can actually see something as faint as a planet, which is reasonably close in the galaxy. But that's not the problem. The problem is one of contrast. And the way I try to explain this, people, is the analogy of baseball. You might be able to tell from my accent I'm not from here. There's a few bits of American culture I've had to learn. Some bits I like, some bits completely mystify me, and baseball is definitely in the latter category. Nothing ever happens. I was taken to a baseball game by an utter fan, and he was explaining all this stuff. You see the way the batter's doing this? You see the way the pitcher's doing this? No, I don't. Finally, the guy with the big stick hits the ball into the air. I say, finally something's happened. Everyone goes, oh. It was a fly ball. Goes up, guy puts out his mitt, the guy's out, right? Easy to catch a fly ball. Even I know that. It's not easy to catch a fly ball if the fly ball is coming out of the sun, right? Why is that? It's not that the ball has suddenly disappeared. It's not that it's any fainter than it used to be. But the contrast, it's lost in the glare of the star. And so you can't see the ball because your eyes are completely blinded by the light from the star. This is the exact problem we have when we go looking for planets. We could detect the light in principle, but there's so much light coming from the star that trying to see that extra little blip that's coming, reflected light from the planet, is just not enough. Now, it's not impossible to do, as this picture shows. I've just said it's really hard to do this. Here is a picture of a planet around another star. This is called 51 Eridani. It was discovered by the Gemini Planet Imager, which is led by a group out of Stanford just up the road. And what they've done here, they've gone through a number of complicated techniques, which I'm not going to explain, to block out all the light from the central star, which is right here. Little bits of it sort of leak around the edge there. And when they block out the light from the star, they can reduce that enough that they can see the light from this planet here. This is really amazing. This is not the first image of an extrasolar planet that's been directly imaged, but there's only a handful of them, and it's really a technique which is only about 5 or 6 years old in terms of its success. So we are the first generation of people who are able to see planets around other stars, and I think that's really amazing. But this is not the way we're going to go find Earths. You'll see there's a couple of things about this planet which don't make it Earth-like, at least by my definition. One is, based on the brightness of the planet, they can sort of make a guess at how big it is, how massive it is, and it comes out to be about twice the mass of Jupiter. It's a Jupiter-like planet, it's not an Earth-like planet. The other one is based on this dashed line, you can see it's actually quite far away from its parent star. It's further out from its parent star than Saturn is from our own. If you want to find an Earth, you've got to find something which is about 1 million times fainter and about 10 or 20 times closer in. We can't do that yet. People are working on that technology. I'm not saying it's impossible, but if you want to have answers now, you've got to think of some different technique. And the technique that Kepler uses is called transits. So imagine for a moment that you're an alien astronomer, you're sitting on a planet out there in the galaxy, and you're staring at this planet, this star, which according to your star book is called the Sun. And if you're very careful, and if you're very patient, and if you're looking very carefully, and at just the right time and at just the right angle, a planet might pass in front of that star just like that. Now you won't be able to see the whole star. All you will see is that something has blocked the light of the star, and the brightness of the star seems to have been reduced by just a little bit. And if you're really patient and you wait, what is the orbit of Jupiter? 11 years. So you keep watching this star for 11 years, you might be lucky, and the same thing happens again. You could look at all these dips, and you could conclude that something is in orbit around this star. It's periodically passing between you and the star. It's blocking out some of the light. And you could say, this thing, based on its size, the amount of light it's blocked out, that it's a planet. Now, if you're a really careful observer, you might notice that there's more than one planet in this system. But it's going to be hard to detect the Earth because the Earth is about 10 or 11 times smaller than Jupiter. So to scale, this is what the Earth would look like. It's not very big, is it? It doesn't block out a lot of light. It blocks out about 1 part in 100,000 of the light. In the meantime, the star has got sunspots. These things are much bigger than planets. They also block out some of the light, so they're causing change in the light structure from the star. You've got boiling, bubbling gas on the surface of the star. That's changing the brightness as well. So this is not an easy measurement to make, but it is, in principle, doable. This is the transit method, and it is surprisingly extraordinarily old. It was first suggested in an amazing paper written by an astronomer by the name of Oddest back in 1952, 60 years ago. In this one paper back in the 1950s, he suggested both the transit method and the other method you've probably heard about, which is the radial velocity method. He suggested these would be 2 great ways to find planets. And it took us about 50 years for the technology to catch up with it. As great as this idea is, it's not a wonder solution. It's not a silver bullet. It has its limitations, and those limitations are important to understand. For one thing, as I've just pointed out, if you're looking for planets like the Earth, they don't block out a lot of light. So you need a really sensitive detector. You need to eliminate all your other sources of noise. The transits only happen once a year. The planet goes around. It comes back. So it's easy to see short period planets because they come around every few days. It's hard to see long period planets like the Earth because they only come around once a year. And if you take a break at just the wrong time, you'll miss that transit. You'll have a year's worth of data on a star and see nothing. So you need to have a long survey that's as uninterrupted as possible. And that's extremely difficult to do from the ground because if you've got a telescope on the ground, half the time it's pointing in the wrong direction and the sun is up. It's good to go into space for this sort of thing. The other thing is that, the planet's going around like this, it blocks the light. What if the planet's orbit is actually like this? It will never pass between us and the star, and we'll never see a transit. So it turns out that 99% of all planets that are out there in the universe will never have their alignment just right for us to see a transit. So if you want to detect planets this way, you've got to look at hundreds of stars. You've got to look at about 100 stars for every planet you hope to detect, even more if you want to find things as far out as the Earth. And transits yield limited information. So here is a light curve. Here's time series data of the brightness of a star, and this star has a planet around it. So each blue point you see in this time series represents the measured brightness of a star at a certain time. And you can see that there's these periodic dips here, 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 here. That's the transit. That's the signal of the shadow of the planet as it passes in front of the star. Now we can learn a few things from this. From the depth of the dip, we can work out the size of the planet. Big dips, big planets, small dips, small planets. From the time between the dips, we can work out how long it takes the planet to go around once. From that and the properties of the star, we can work out the separation between the planet and the star, the semi-major axis. And from the semi-major axis, the distance, and from the properties of the star again, how bright it is, how hot it is, we can sort of get an idea of what the temperature is on the surface. Now, that's kind of complicated because we can work out the temperature on the surface if there's no atmosphere. As you know, habitable planets tend to have atmospheres, and atmospheres tend to have a greenhouse effect. So you can sort of say, well, if it has an Earth-like atmosphere, it'll add this many degrees to the temperature and so on. You can get a handle on the temperature. And that's all we get from the transit method. And this explains the definition I gave you earlier of an Earth-like planet is basically the size and the temperature, because these are things that we can actually measure with the transit method. It's a very convenient definition. So this is the instrument that Bill built. It's a very simple thing to understand. It's basically a big tube. At one end, you've got a mirror. The mirror reflects light onto this thing here, which is a big CCD chip. There's very little going on. Bill, I have this quote which I use, and I'm not sure if it's real. You once described this as the most boring thing NASA ever launched. Is that true? Most boring mission. I didn't say mission. I said space. Yeah. Boring is good if you're an engineer, right? Boring means there's fewer things to go wrong. And there's very few things in this. Everything is very simple, and that helps it do the same thing over and over and over again, which is what we want. This is the key part of the telescope. This is the CCD camera. There's 42 chips. Each of one is a CCD camera, just like you have on a phone. It's a whopping 2 megapixel camera. You say you might have that beat, but we got 42 of them, right? So we got you beat. It covers an enormous patch of sky. Remember I said that the Hubble field is like a grain of sand held at arm's length? If you held up your hand like this, that covers about the patch of sky as what Kepler covers, about 115 square degrees in total. Let's see, what do I want to say next? I could go into the details of CCD camera. Given the time I have, I'll probably avoid it. This is now our big data problem. We have this telescope. It's got 42 of these, 2 megapixel CCDs. There are 84 megapixels in total. We expose once every 30 minutes, so we get 2 exposures every hour. If you add that up, that's 121 gigabytes per month. I can see you're shivering in fear of it dealing with that much data all at once, right? Who here goes through 121 gigabytes in a day? So we get all excited about this. But then you have to remember that we have a spacecraft which is in space. It's not even in orbit around the Earth. It's in orbit around the Sun. It's many millions of kilometers away. So our bandwidth from there is pretty low. It's better than dial-up, but it's only about 4 megabits per second. At 4 megabits per second downlink, we are collecting data faster than we can possibly download it. And that doesn't work. So what we do is we only select the pixels which are immediately around about 150,000 of the most interesting stars in the field. So we pick out in advance which stars we want to look at. We save the data in a small box around those. And after compression, we get that down to about 5 gigabytes per month, which is conveniently about the amount of data we can download in the time that NASA will give us to download our data about once a month, using this dish right here, which is just outside of LA. So we have our telescope, we put it in space, we take all these pictures, we download the data, we measure the brightnesses of all the stars. How do we find planets in this? And this is where, if you're coming in hoping for a non-technical talk, I might start to lose you a little bit. I'm going to start going into some of the more technical details. If you get lost along the way, don't worry, I'll come back up from here on the other side. So this is the principle that we use. So here's an example light curve showing a little dip here, and that's your planet. And this is just purely simulated data to get the idea across. The idea that astronomers use, a technique that we use, is called Boxley squares, or there's a variation that we use called TPS, which is transiting planet search. But the idea behind it is simple. You create a time series where each point is the average of all the nearby points, for some definition of nearby. This is the effect of smoothing out all the noise you get from all your other from where there's no transit, but it preserves the signal of your transit pretty well. So this gets down the noise, it amplifies the signals. Then we take this Convolve data set and we fold it at some period. And if there's a transit in there, if there's a planet with that period, all those peaks in our convolved light curve will line up, they'll combine constructively, whereas the noise will sort of cancel each other out. So we'll go through this, we'll fold it a succession of different periods and trying to find these peaks. For those of you who are computer scientists, I did 2 whole years of computer science in college. The only thing I remember is my big O notation, and if that is still something that's important for people in computer science, this convolving step is of order n. Right? It's very simple. You run this thing across the data, whereas the fold and search step is of order n squared. So the more data we collect, the time it takes us to search these light curves goes up with the square the amount of time we've been collecting data. Now this works if you've got nice, smooth, clean data like I've been advertising. Kepler, when the data comes down, and I don't want to insult the telescope, it's my favorite telescope in the world, but the data does not come down nice and clean. We've got all sorts of bumps and wiggles and jumps and weird things going on. And I'll walk through a couple of these because it's kind of interesting to think about what actually goes on in the spacecraft and how that affects your data. So can you see this big curve here? What's going on is we've got to download our data. And to download our data, we've got to stop observing our field, where we're looking at our planets. We move the spacecraft around so the antenna is pointing at the Earth. And when we do that, the sun starts shining on different parts of the spacecraft than it was a little bit beforehand. So some things warm up and some things cool down. And when things warm up, they expand. When they cool down, they contract. And so the position of that CCD camera I showed you earlier moves around just a little bit. Microns, millionths of a meter. But it's enough to change the focus of the camera. And then when we point the spacecraft back to the field, all that heat has to get redistributed, the focus changes, and that causes the measured light from the star to change. In most of these stars, the light gets refocused, and so the star gets brighter. In some of our stars, it's a big field of view, our focus is not perfect. The star actually looks better when it's in our out of optimal focus position, and it looks worse in our ideal situation, and so the light from the star actually gets a bit fainter. It's a bit funny, but when you've got a big field of view, these are like the trade-offs you have to do. The other thing we have to worry about, I'm not going to go into all the details, but can you see there's like a scalloping or a ribbing through the data here? What's going on here is we have to point this telescope, we have to point it in one place all the time. We have these momentum wheels, reaction wheels we call them, inside the spacecraft, and they spin up to absorb the momentum we're absorbing from the sun. As these wheels spin up, they get hotter. That heat somehow, despite everyone's best efforts, leaks into the rest of the spacecraft and changes our focus a little bit. And then after about 3 days of this thing spinning up and getting hotter and hotter, we fire the rockets, we spin down the wheel, it gets cold again. And so you can see that 3-day signal in your data. It's kind of a bad thing. This is, I haven't put it in here because it doesn't look very good, but the amplitude of that ribbing is higher than the strength of the signal of an Earth-sized planet you might want to find in that data set. So it's a big deal. It's something we have to worry about. We have to take all this stuff out. And the approach we use is variously called single-value decomposition or eigenvectors or principal component analysis or something like that. So I've got a plot here of a series of light curves. These are all light curves about the same brightness, about the same part of the sky. And you can see they're all doing weird and wonderful different things. But if you look closely around here, say, you can see that they've all got this tail off after the gap in the data. That was the monthly download, the heat's redistributing, the focus is changing. They've all got something over here where there's another blip in the light curve, and they all sort of respond to it the same way. So singular value decomposition, without going into the mathematics of it, because I know I don't understand all the mathematics of it, it basically finds the most common trend in all of our light curves. And it creates a light curve based on that. We can then take this, which is the eigenvector, we can subtract that off from all our individual light curves and remove those systematic effects. Exactly how we do that in the Kepler data is described in a couple of papers from about 3 years ago by Jeff Smith and Martin Stumpa. It works rather well. As you can see, here's the data set I showed you before. Here's the data after correction. You can see all these bumps, blips, and wiggles have all gone away, for the most part. This has been an enormous success. This one piece of technology has really enabled us to be able to find these planets, to get rid of all these systematics which are perfectly quiet spacecraft is adding to our data because nothing is ever perfectly quiet. SVD is of order mn squared in terms of its running time. So n is the number of data points you have, and m is the number of light curves you're working on. So if we did this on all 150,000 stars for all 4 years a day that we have, the whole thing would be computationally intractable. So we break it down into chunks of about 3 months, which is the time in between. I get to where the 3 months come from. And like each CCD we do at a time. So every 90 days in blocks of about 2,000 stars. Okay, even after we get rid of all those large-scale systematic signals, you think finding planets should be easy. It turns out that really good data, when you have a large search like this, has a lot of false alarms. And this is where I'm probably going to lose half of you, but bear with me. If you deal with noisy data, if you do any sort of science or dealing with noisy data, you have this concept of sigma, which is detection significance. And the best way to think about this is how strong is the signal you're seeing compared to the average noise in your data. If you're a psychologist, if you work in what we like to call the soft sciences, you typically see 2 sigma being given as a threshold for a statistically significant interesting result. 2 sigma means, and definitions vary, so if you know what I'm talking about, bear with me. 2 sigma means there's a 2% chance of seeing a signal that high due to noise alone. That seems pretty small. Astronomers, we're hard scientists. We say 3 sigma is, the benchmark for detectability. That means there's less than a 0.1 chance of seeing a signal that high because of noise alone. Particle physicists are really hardcore. If you go down to CERN, they get all these collisions that they're measuring data in. They insist on 5 sigma. They say, we're not convinced this is real unless there's 1 chance in 10 million that this thing is real. With Kepler, because we're looking at so many light curves, because we're folding at so many periods and looking at so many different phases, if we use the particle physics hardcore 5 sigma detection threshold, we would expect to see about 400,000 false alarms just due to this white noise alone. So we end up going up to a threshold of 7 sigma, which even beats those, what do you call them, the motivational speakers about how to do excellence in software, the 6 sigma people. We have them beat. Oh, but were it that easy? So after we remove all our systematics, all our gross common systematics, after we impose a really high threshold on the sort of detections that we want, when we run our pipeline, which does all this stuff, and which is not something that I myself work on very much, we end up with about 20,000 events coming out of it. And we've gone through this a number of times on our 7 catalog. We know that we expect about 4,000 planet candidates on the other side. So even after we've gotten rid of all these things that we can think of, there's still a lot more work that goes into looking at these 20,000 detections and figuring out which ones are the real ones and which ones are the various kinds of false alarms. This is what is involved in producing the planet catalog that I'm here to talk to you about today. And I'm going to spend most of the rest of my talk discussing the various problems that we've encountered and the fixes we've come up with them. One of the things that I'd like to sort of point out, because some of you are technical people who will work in astronomy, and if you understand one thing about the catalog, understand that we err on the side of passing things when we're in doubt. We err on the side of saying this thing might be a planet unless we have definitive evidence that it's not a planet. So after watching a couple of episodes of Law and Order or SVD or something like that, or SVU, I come up with the phrase innocent until proven guilty. This is the principle we apply to our catalog. We err on the side of keeping things in instead of throwing them out. This means our completeness is very high. The probability that a real planet passes through our catalog generation process is very high, but our reliability is kind of low, because stuff that is not real, stuff that is just some sort of junk in the light curve, some of them will sneak through our net. So the first problem we have, we call eclipsing binary stars. So we're looking for transits of planets around stars. It also happens, it's been well known for many decades, that you also have stars in orbit around other stars. Now, these are really cool to some people. Some people devote their lives to them. We're not interested in them. We want to cull them out of our catalog. And the way we do this is if you've got a star going around another star, if it's passing in front of it, it blocks out light from the brighter star and it produces a big dip in your light curve, like this one here. When the smaller, fainter star then passes behind the bigger star, you get a smaller dip when you lose the light from it. It's called an occultation. And so we see a second dip. This is one of the most common things that we have in our catalog, which are not planets. And they're really very easy to take out for the most part, because you can just look at this and say, oh, wait, there's 2 dips at the same orbital period. That's not something I'm particularly interested in. Unfortunately, not all eclipsing binary stars show this secondary event. So one of the other things that we do is we go back and we look at the pictures in which the light curves were created. And we take a difference image of the light that we see in transit and out of transit. We subtract the two and we see where is the light changing in this image. So what I'm showing here on the right, somewhat confusing, is a picture of a star, a relatively bright star. And you can see this dotted line here says, these are the pixels where the light from our star dominates. We take a picture of this star in transit and out of transit. We take the difference, we subtract them. You get this picture over here. And you can see that the light is concentrated on this much fainter star over here in the corner. And so this does not look like an eclipsing binary star when you just look at the light curve. It doesn't have that secondary event, but we can pick it out this way. And we have a couple of other techniques as well that we use. Then there's variable stars. For every variable star you can think of, someone has done a PhD on it, possibly many PhDs. They are all sorts of weird and wonderful, and they're vermin. Most of them are periodic in some sense, and if you run some sort of an automatic algorithm which is looking for periodic events, they look like periodic events. We've got Cepheid stars. These are beautiful, big, giant stars that are getting brighter and fainter as they swell up in size and then shrink down in size. And they swell up in size and they shrink down in size. Really beautiful things. We've got spotted stars. I showed you earlier a picture of the sun with the star spots. It's like a scuff mark on the surface that comes into view and goes out of view again. And that produces a very periodic signal in your light curve as well. This is a red giant star. If you have heard anything about astronomy, you've heard of red giant star. This is a star which is on the verge of dying. It puffs up to enormous size, and it vibrates like a bell which is ringing in many, many overtones simultaneously. And so you get this really messy, ratty light curve. There are people who love these things. By looking at the exact frequencies that this thing is vibrating at, you can infer all sorts of properties about what's going on inside the star, what sort of chemicals are being produced on nucleosynthesis in there. Some people love these things. They're trouble for us. We've got cataclysmic variable stars. We've got a few of those. This is just a star which explodes every couple of days for reasons best known to itself. No one ever understands why these things choose to explode when they explode. We've got a good idea of where the material is coming from. That's another matter. And then there's this thing. When we saw these things in our light curve, the thing that came to mind is you watch the medical shows, you watch ER or something like that, and they got the guy hooked up to the heart monitor and it goes beep, and there's a little blip. So we call these heartbeat stars. And if there is someone in the audience who gave a SETI talk on this a couple of weeks ago, if you're really interested in those, have her back, she'll do it again. So this is how we found these things. We painstakingly would go through thousands and thousands of light curves. We trained up a team of astronomers to look at each one. We told them what to look for. They would come back and say, I saw this, it didn't make any sense. We'd go and we'd tell people to look for this new thing as well once we figured it out. It was a very slow process. It was a very educational process. It was a very fun process. But it had the problem of humans are not robots. We don't do the same thing over and over again. If you've had a good day, you're really enthusiastic, you're going to find lots of planets. If it's a long time since you've had coffee, you're just not going to be concentrating as much as what you do. So we call this problem the CCCC, the caffeine consumption correlation coefficient. And we realized that we had to solve this problem, the CCCC, if we were going to be able to turn our lists of planet candidates into something where we can establish the occurrence rate, the frequency of planets out there in the galaxy like our own. So instead of going through a human method, we said we're going to have to sit down, we're going to have to write computer programs to mimic what the humans are doing. And that's going to be easy, right? Writing computer code is easy. So we spent about 2 years at it, on and off, and we have something now which works pretty well. And I'm going to walk through some of the ideas of the algorithms of what we came up with that makes this work. The first one, of course, is the eclipsing binaries. The eclipsing binaries, if they got that secondary event, it's easy to find. So you have this folded light curve, you convolve it, you find this big peak, you say, okay, that's where my planet is. You then say, is there a second peak in this light curve at that same period? If there's a second peak, there's a good chance that that's an eclipsing binary, and that's how we find those things. That's really easy to do. The thing where we found the stars in the background, we found a way of automating that where we would sort of measure the location of the brightness of the star and how it shifted during the difference image. I tried, this is like one of my major contributions to this automating the pipeline, and I cannot come up with a good slide to describe it, so I'm just going to skip over it. No good plots. Instead, I'm going to talk about something, the way we detected variable stars. So this is a really cool, a really neat technique. We call it the Lpp technique, which is really misleading because that's sort of a minor component of it. But this is how it works. So I've got two light curves up here, one of which is a light curve which has got no transit in it, and this one with the red dots has got a transit in it. I'm going to represent these two light curves in the simplest possible way. I'm going to take one point representing the brightness before transit, one point that's in transit, and one point that's after transit. So I've collapsed that light curve, all that information down to just 3 values. You then take those 3 values and you project it in a 3-dimensional space. So this value is close to 0. In the second dimension, you're negative. In the third dimension, you're close to 0. So things that have no transits in them are all going to cluster around the origin in this 3-dimensional space down here. Things that have transits in them are all going to cluster in sort of a point down here, negative space in your second dimension. And the key word here is cluster, is you can sort of draw circles or boxes in this space and say things that lie around here have no transit in them, things that lie down here have transits in them. I haven't shown it here, but the key idea is that your variable stars, your various different kinds of variable stars, are all going to cluster in different parts of this parameter space. And so you can take a light curve that you haven't looked at and say, well, it ends up in the same part of parameter space as the Cepheid variable, so this must be a Cepheid, or this must be something that has star spots. So here's a slightly more complicated cartoon example. It's still just a cartoon example. Instead of representing a light curve with 3 data points, I'm now representing it with 20 data points. I've got 2 simulated transits up here and 2 simulated variable stars. These are just sine curves, a little bit of noise added into them. So I project these into now a 20-dimensional space, and then to improve the clustering properties in that 20-dimensional space, I use a technique called locality preserving projection to map that onto a 2-dimensional space that you can plot on a screen. And you can see that these things here are all simulated transits that we've injected, and they cluster on the right-hand side of the diagram, whereas the variable stars cluster on the left-hand side of the diagram. The LPP, the locality preserving projection, has this neat feature that as it does this compression, it makes sure that points which are close to each other in the high-dimensional space end up close to each other in the lower-dimensional space. And this makes the clustering part of it quite a bit easier. So what we ended up doing in reality is we bin our light curves into 141 points. We then project that down into a 20-dimensional space. And then some of the light curves that we put in, we pre-label, so we know these things are transits, these things are variable stars, and so on. And we say, okay, how close are you to the nearest cluster of transits? We call that what I call it here is the transit dissimilarity index. So all these red points on this graph are known transits. And you see all the known transits cluster at small values of this, mean all the transits ends up somewhere in the 20-dimensional space, which is close to other transits. The purple things, which are known variable stars, all end up at distances, at much further distances from clumps of transits. And so once we have this plot, we can just draw a line here across the middle of it and say, if you're below that line, you're close to the transits, and you look like a transit. If you're above that line, you look like a variable star, we're going to throw you out. You're not a planet. And we've done this. We sort of, we trained in a labeled data set. We tested in a set. It worked well. We then injected some planets into and made sure that everything still behaved itself. It all worked out quite very well. And we can rule out most of the variable stars using this while losing only a very tiny fraction of the actual bona fide transits. Don't look at those. Okay, I'll come back to them. So something that we found when we're doing this, we're looking for eclipsing binary stars. We sometimes found that we've got light curves look like this. There's a statistically significant peak in here. And so the pipeline was looking for transit says, hey, I found something here. It's statistically significant. It might be a transit. Can you see it? Not really. It's buried in the noise. There seems to be all sorts of statistically significant peaks all going on in this light curve all the time, even though we've done a very careful job trying to estimate our noise. And what's going on here, it's one of these things where you really have to go back to the very start. So we have a spacecraft, and it's got a solar panel on one side of it. As the spacecraft is in orbit around the sun, it will eventually end up, the solar panel starts on the sunward side, it ends up pointing out into space. We get no power from the sun, our spacecraft dies, and the telescope heats up and everything gets destroyed. So what we do is every 3 months, quarter way through the orbit, we rotate the spacecraft 90 degrees so the solar panels are pointing at the sun again. When that happens, a star that was being observed on this CCD, this is the box, is then observed by this CCD, and then 3 months later by this CCD, and 3 months later by this CCD. That's all fine and good, except that some of the CCDs we use have got a bit of a problem with the electronics inside, and they're imprinting this wavy pattern over the data. It's a very low amplitude wavy pattern. If you weren't looking for signals of small planets, we wouldn't care about it. But it has the problem that it's a small pattern. It shows up once every year, once every 4 times around, and so it looks exactly like this, very close to the signal of an Earth-like planet in a 1-year orbit, which is somewhat unfortunate. And if you look at this, we put these through our LPP algorithm, and it marks out some of them. It says some of these things really do not like transits, but some of these things really do look like transits. And if you go look at those light curves, you go, that really does look like a transit. If you just take that photo light curve, you look at the transit, it's got the right shape. It looks like what it's supposed to. And so we have a hard time saying, what's going on here? How do we reliably take these things out while preserving the actual transit signals at the periods that we're particularly interested in? And one of the things we've hit upon is actually very simple, is we say that this signal here might be statistically significant, but it also has to be statistically significant relative to all the other peaks that we find in our convolve signal. Nice simple technique. It ends up working really, really well. And then finally, despite all our best efforts, most of our things which try to remove systematics which are common along long-term trends. So we see it in this light curve, we see it in that light curve, it takes days to happen. You just get bumps and wiggles in your data, no matter how careful you are. And so you can see this was a thing which lined up with, I know this is a small snatch of a time series, a couple of days long. It lined up with a small snatch of a time series about a year later, where the light curve was doing this, and then it jumped up. And so if you fold the convolutions together, you get something which looks a lot like a big peak. And so what we do is, for these small things in the long periods, we go in and we look at the individual events, we fit them with a model of a transit, and we fit them with a model of a couple of systematics that we've seen in our data. And then we use a Bayesian information criteria, BIC, to see which thing is more likely for this event. Does this look more like a transit than it does one of our known systematics, or does it look more like a known systematic? And this works rather well, but it turns out when you're down at really low systematics, everything looks sort of like everything else. And so this rules out a few more things, but it doesn't catch everything. We're able to simulate, now that we've got an algorithm working, we're able to simulate it. We're able to test it by injecting signals and see what a good job it does recovering them. This was very hard to do with humans, because it's very hard to say to a human, okay, here's some simulated data of a planet. Now, vet it like you would as if you didn't know if it was a planet or not. Everyone wants to be right. Deep, deep down subconsciously, you want to get the right answer. So if you know the right answer is it's a planet, the chances of you saying, well, it's probably not a planet, are very small. The testing the humans was really hard. Testing the algorithms is much, much easier. So we injected planets with a whole bunch of signal to noise. And for a reason I won't go into, when we say signal to noise in Kepler, we use the acronym MES for multiple event statistic. That's all that means. We inject them a whole range of periods. And this plot is saying, after we run all these things through our catalog generation tool, what fraction of them do we correctly label as planets? For high signal to noise things, it's usually very easy to detect that it's properly a planet, and so all these things pass. We've got some low number statistics over here, and so if we get one thing wrong, it looks really bad in that bin. As you go down to very low signal to noise, very long period things, you're getting into that regime where it's very hard to tell the difference between, is this a bona fide planet, or is it one of these wavy patterns that's been imprinted on our signal by the detector? So our completeness goes down fairly well. It goes down just a little bit. But overall, we're very happy with this. We're doing a very good job. So in terms of completeness, we're doing a great job. If there's a planet in there, we tend to let it go through and include it in our catalog. The other side of this is reliability. And reliability is a little bit harder, excuse me. So what this histogram here is showing you is the number of events that were found by the pipeline for this catalog as a function of period. And it's given in log periods. So there's 10 days, there's 100 days, there's 1,000 days. Most of the things that we find are at extraordinarily short periods, less than about 10 days. And these are mostly variable stars of various shapes and kinds. We also get peaks out here due to this amplifier problem, what we call rolling band. And also the fact that if you've got little bumps and wiggles in your light curve, the chance of you being able to line them up just right improves as you go to longer and longer periods. That's what's causing this hump here. The blue histogram then is showing what remains after we do our vetting. So we do a very good job taking out all these short period things, thanks to the Lpp algorithm. We do a very good job taking out these things, and we get a shape which looks roughly astrophysical. That's sort of kind of what we would expect to see. The planet distribution peaks at about 10 days in this, and then as you go out to longer and longer periods, we're getting the chances of it transiting getting smaller and smaller, and so we're detecting fewer and fewer things as we go to longer period. That's kind of as we expect. We do still worry, so we're doing a good job. We're getting rid of loads and loads of stuff, but we're still worried that a few things are leaking through. And we expect a few things to leak through. This plot here is showing, again, the number of KYs. This time it's a log-log plot. This blue line shows sort of an optimistic idea of what we'd expect our planet population to do. If you took the most optimistic thing you could say for planets, saying the probability of finding a planet at a given orbital separation, a given orbital period, is about uniform. It doesn't matter if you're close in or far out. You should get this line here. And what we actually get is we get more planets passing through, or more events passing through, which we're claiming planets at these long periods. So we still think as you go out to long periods where you're particularly interested, and for small planets where you're particularly interested, we're not getting rid of enough stuff as we go along. And so we're probably overestimating occurrence rates there if you don't do your work very, very carefully. So this is the catalog. And I'm running short of time, so I'll breeze through this a little bit quickly. This is showing in blue all the planet candidates we found from all our previous catalogues. The yellow is everything that's coming out of the 7th planet catalogue. You can see over here there seems to be sort of an overabundance of things just out here, small planets, long periods. This is the reliability problem I'm talking about. This is something that we're still working very hard on. The other thing that I would really want you to take away from this plot is how most planets seem to have radii somewhere between the Earth and Neptune. 2, 3, 4 Earth radii. This was unexpected. There's nothing like this in our own solar system. If you go back to theory papers from before Kepler was launched, they specifically predicted that this would be like a barren area. You wouldn't find these intermediate planets. They'd be very, very rare. So this is something of a surprise to us. And one of the big results that's come out of Kepler, and one of the things that's going to make us people have to go back and redo their formation models. Of particular interest are the small things at the right distance away. This is giving you an idea of what these are. I've changed my axes again, I apologize. This x-axis here is the energy received by the planet in units of the amount of energy the Earth receives from the Sun. So the Earth receives 1.0 on this. Something receives a tenth the flux of the Earth is down here at 0.1. The y-axis then is the temperature of the star. So up here are stars like the Sun. Down here are cooler stars, much smaller stars called M stars. Just to orientate you, this is where Venus, Earth, and Mars lie in this diagram. Then the green band here is someone's theoretical prediction of what is the right distance away from the star to get liquid water. What is the habitable zone? And that's a theory line. It should be taken something with a grain of salt, but it's sort of something to work off of. The blue circles are stuff from the older catalogues again. The yellow circles are stuff from the newer catalogues, or from this new catalogue. Filled circles are things that have been confirmed in some way. Someone has gone out, really studied this star, come up with independent evidence to back up our claim that there's a planet there. These things are stuff that is almost certainly like 98, 99% probability of being real. The open circles are things where that work has yet to be done. And a little bit of caution for these open circles, while they're exciting, well, there's a lot of them there, until someone goes and does that follow-up, our ability to estimate how much energy this planet is revealing is actually pretty low. So that would be the error bar on one of those open circles. So people have to go and follow these things up. The things which are too cold might end up warming up. The things which are too warm might end up cooling down a bit when you know the parameters a bit better. Things move around a bit. Which brings me, I suppose, to my big caution, which is don't believe the internet. And this is something I sort of struggled with a little bit because this is really cool. We want to tell people how cool it is. But when you go through the process of going from science to press release to newspaper article, subtleties and nuances tend to get lost along the way. So as a scientist, this is what we see. We see a light curve. We see a little dip in it. We measure the size of the dip. We measure the time between the dips. We work out some properties. This might be a false alarm. We do some work to try and rule out the most obvious cases. We don't think we get them all. Someone goes and does some follow-up work and say, OK, I think this really is a planet. I've got some independent evidence. I've got some statistical argument, something like that. Let's write a paper. It's a very interesting paper. Let's write a press release so everyone can hear about it. They write the press release. They have the press event. They don't show the press this light curve. This is what they show the press. A rocky planet. It's got clouds, it's got water, it's got deserts, it's got grasslands. There's reasons you can sort of say, it's a reasonable thing to say that based on the size of this planet, it's probably rocky. Based on the temperature of the planet, there's a reason to believe if there was water on the surface, the water would be liquid. But what happens is that this is a perfectly reasonable scenario for what this planet would look like. It's one of millions of perfectly reasonable scenarios, some of which, dare I say, most of which are not consistent with a planet with clouds and water and the like. So the press get that. The reporter writes up a story. It goes to his editor tries to amp it up. He puts it out. It goes on social media. By the time it gets onto your Facebook page, it looks more like this. Please, the next time you see Kirk in your Facebook feed, think data. Remember what's happened along the way. But there are some results that have come out of Kepler which we're willing to stand over, stuff which is really profound and really important. And the time I have remaining to you, I want to just give you an idea of some of those big picture results which is coming out. And the biggest one, to my view, is this, is that based on Kepler work and based on studies people have done, the best guess is, and I think we can stand over this, there are more planets than stars in our galaxy. And think about that for a moment. 20 years ago, we knew about one planet. 10 years before that, looking for planets was a little bit airy-fairy, fuzzy-wuzzy stuff. People looking for extraterrestrial intelligence were sort of looked at a little bit askance. There's no real evidence for this. We've now gone from that to the stage we can say that there's more planets out there than stars. It is a fertile galaxy from that perspective. And remember that the next time you look up at the stars, think of the planets that you can't see. The other side of that, so that's one term of the Drake equation that I introduced earlier. The other one is the number of these things that are Earth-like. And this doesn't have any fancy graphics. I'm going to try and walk you through this because it's a very complicated plot, but a very informative one. And it gives you an idea of the limitations, the potential of Kepler data, the limitations that we have to work with, the work that's still to be done. So someone took all the planets that we found. This is a paper by Chris Burke that came out this year. He looked at all the planets that we found. He counted up the stars of which the noise was small enough that we could detect those kind of planets. So he says number of stars that we found, or number of planets that we found, number of stars that were sensitive to that kind of planet. And he did a statistical analysis. He says, based on that, what fractions of stars were we sensitive to Earth-like planets in which we found them? You do a statistical analysis, you come up with an error bar. So he gets this histogram shape of his probabilities. His probabilities are written across the top here in linear numbers. So he gets, the mode of this distribution is somewhere around 7%. So the most likely number he found for the fraction of stars that host Earth-like planets is about 7%. And of course, there's an error bar in that, right? There's always an error bar. But then Chris did something that all good scientists should do. And when it comes to exoplanets, not all good scientists actually get around to doing. He started to question his assumptions. He says, what if all the stars were a little bit bigger than I thought? Or what if they're a little bit smaller? Or what if we didn't do a good job correcting for this than I thought about? Or what if we were overly aggressive doing the following? And so he ran through a series of scenarios and says, how would these scenarios affect my result for the number of Earth-like planets out there, the fraction of stars that are Earth-like planets? And he gets all these histograms. And so while the mode of this distribution is 7%, an optimistic number is maybe 25%, maybe higher. The pessimistic number might be down around 2%. There's a big difference between 2% and 25%. If you put money down on the 49ers getting to the Super Bowl and you were told there's a 25% chance of it happening, and then you woke up the next morning and someone told you there was a 2% chance of it happening, you would not be a happy person. Actually, are there any 49ers fans in the audience? You'd probably be happy with a 2% chance this year, right? 2% is a conservative number. Let's stick with the 2% number for the moment. It would be lovely if it's higher, but I think we can stand over 2% and say it's not going to be any smaller than that. So going back to our Drake equation, we can now sort of fill in these two numbers. We've got the fraction of stars that host planets is greater than 1. The number is somewhere between 2 or 3 would be my best guess of where that's going to end up. Excuse me, that's my phone. Yeah, it stopped. We've got the product here I gave, FP multiplied by NE is somewhere between 2 and 25%. And so 10 years of work, 20 years of work by Bill Barucki, $600 million spent by the NASA taxpayer, I can tell you 2 numbers. I really hope you think those numbers are very important and were worth the time and all the effort. But let me put those numbers in perspective. There's about 100 billion stars in the galaxy. Of those, about 1 million are similar to the Earth in some way, depending on how you want to draw your lines. If our pessimistic number, if our 2% number is correct, 2% of 1 million is 20,000 planets. So there are about 20,000 planets which are Earth-like, or earthy, according to our definition. Similar in size, similar in temperature, similar to a host star. If you take those 20,000 things, you sort of do a Monte Carlo distribution, you spread them around the galaxy. The nearest one is, it's probably around an 8 magnitude star. It's something which is too faint for us to see with the eye. If you went out with a pair of binoculars and you scanned the sky, you'd probably see a planet which hosts, you'd probably see a star that hosts a planet like our own. Now, whether that star has water on it, whether it has an atmosphere and all those things, we don't know. That's future work for NASA. We'll probably get to that, the answer to that in about 20, 30, maybe 40 years. And so that, I suppose, is my take-home message, and I kind of like to leave it there. So I think we have a little time. Maybe we could ask some questions, if people have them.
Thank you, Fergal. That was wonderful. So, I'm kind of a hardware guy, so I like the pictures of the telescope and the satellite dish, and I'm all about transmitters and receivers. But it was really fun to see the Microsoft eyes light up when all the data was being displayed on the screen. So, anyway, so we'll try to truncate the questions a little bit because we've gone a little over our time. So let's do like about 4 questions. If you have other questions, you can reach Fergal through our website and through email. we'd be happy to address those questions a little bit later on. So questions over here.
So the star that Bill mentioned at the beginning that has the dips up to 20%, how did you analyze the data and say that's not an anomaly, that is actually a star with dips? Because that's nothing like the light curve of a normal planet.
That's nothing like anything that we know of. That actually, someone correct me if I'm wrong, I don't believe that got triggered in the pipeline as a potential planet candidate because the dips are aperiodic. They happen at different times, and so we didn't see that. How much do you want me to rant about alien megastructures?
You can talk about alien megastructures all day.
I'm a little frustrated by this. Someone found this star. Someone did a great amount of work figuring out what it was, what we were seeing, what it wasn't, and then came up with a paper, and the title of it was, "Where's the Flux?" Work out the acronym there, right? She was very clear. She did not know what was going on. She did not know what was going on. Someone else took the paper and said, look, it's nothing that we can think of. This would be a great thing to follow up at SETI. And so we got in touch with the SETI people and said, you should follow this up with the Allen Telescope Array. So far as I understand, he then got talking to a reporter independently and told him about this really interesting thing that was working on. And before you know it, the Atlantic is saying that we've discovered aliens. What I really love about this, the Atlantic Monthly is saying that we discovered aliens. Turn to page 51. If they really believe there was something going on here, it'd be on page 1, it'd be the cover, right? They'd stop the presses. That should be all that I say about that. I've got to start ranting even more.
Question?
I'm surprised to see that there's only 1 million stars similar to our sun out of 100 billion in our galaxy. 1 in 100,000?
By far the majority of stars are M stars, or dwarf stars. I borrowed this slide from a previous talk where I worked this out, and I can't remember how I did the numbers, exactly how I drew the definition. But definitely the smaller the star, the more common they are. If you go up to like A stars and O stars, really hot stars, yeah, they're vanishingly rare in terms of numbers. But they're much easier to see because they're much brighter.
Just not to say there aren't planets around M stars.
There are planets around M stars. In fact, there are probably more small planets around M stars than there are around planets like our own.
So we're just getting started. Another question.
How difficult is it to determine the plane of ecliptic for another star?
I'm sorry, say again?
How difficult is it to determine the plane in which the planets are in around another star?
Well, there's a very easy way. If you see a transit going in front of it, it's in the plane, right? More complicated, the star itself is rotating. And are the planets orbiting in the same plane as the rotation of the star? There is actually a way of doing that. It's called the Rossiter-McLaughlin effect. You can only do it for really big planets in really small period orbits. These are things that we don't know how they got there. So whatever put them in those things could have disturbed their orbits. Most of those are orbiting in the same plane the star is rotating. Some of them are not. Some of them are even like this, they're basically going the wrong way. And some of them are going like 90 degrees. That might be something to do with the mechanism that brought them in. We've got no reason to believe that these things are in general not aligned.
Yes, there are different kinds of galaxies. Does that change the nature of star and planet formation?
That's a very good question. We don't know. That's my standard answer. There are people who say that elliptical galaxies, so we live in a disk galaxy, it's got these beautiful spiral arms. The spiral arms are full of dust and star-forming regions. If you look at elliptical galaxies, they've got much less dust, and people have used that as an argument to say that spiral galaxies are the best place to go looking for planets, elliptical galaxies are worse. I've talked to people who study elliptical galaxies. Yeah, there's dust there. There's not as much, but there is. And so it's hard to know. We don't know. And we are a long, long way from doing extragalactic exosolar planet studies. Yeah. You have time for one more?
One last quick question.
Just wondering, so the search is limited to
stars in our galaxy?
This search is limited to stars in our galaxy. This search is limited to stars in a narrow pencil beam going through our galaxy along one of the spiral arms. And so we are sort of making the assumption that there's nothing intrinsically special about that part of the galaxy. You may have heard that Kepler collected 4 years of data and then we had some mechanical problems. We repurposed the telescope as K2. It's now pointing sort of all over an arc around the sky. There are very preliminary possible hints from people who admit that they haven't worked out all the details, that statement that this is a represented part of the galaxy might not be true. Planets may be more common in certain parts of the galaxy than others. But let me repeat all those caveats again.
All All right, well, so thank you very much. If you are interested in other galaxies far, far away and a long, long time ago, the Star Trek movie's coming out in December. So. But I'd like to thank our speaker and ask you if you pulled one of these tickets for the books we have to give away. These are signed copies of some relevant and interesting books. Please stick around, and we'll draw those in just a minute. But I do want to present Fergal with the highly coveted SETI Talks Speakers mug. These go on eBay for about $100,000, so they're very rare, and we thank you very much for a great talk.
Thank you. If we sell enough of these, we can build a new Kepler.